Mahamanav Aerospace and Research Exploration Private Limited. This is an internship program on avionics presented by Priyanka Ayali. Global Positioning System. So, in this internship program, we are going to study the introduction to Global Positioning System, working principle, and the uses of GPS. What is GPS and how does it work? The Global Positioning System (GPS) is a navigation system using satellites, a receiver, and algorithm to synchronize location, velocity, and time data for air, sea, and land travel. The satellite system consists of a constellation of 24 satellites in 6 Earth-centered orbital plane, each with 4 satellites orbiting at 13,000 miles, that is 20,000 km above the Earth, and traveling at a speed of 8,700 mph, that is 14,000 km per hour. While we only need 3 satellites to produce a location on Earth's surface, a fourth satellite is often used to validate information from other 3. The fourth satellite also moves us into the third dimension and allows to calculate the altitude of the device. What are the 3 elements of GPS? Global Positioning System is made up of 3 different components called segments that work together to provide location information. The 3 segments of GPS are space, satellites, the satellites circling the Earth, transmitting signals to users on geographical position and time of the day. Ground control. The control segment is made up of Earth-based monitor stations, master control station, and ground antenna. Control activities include tracking and operating the satellites in space and monitoring transmissions. These are the monitoring stations on almost every continent in the world, including North and South America, Africa, Europe, Asia, and Australia. User equipment. GPS receivers and transmitters, including items like watches, smartphones, and telematic devices. So, how does the GPS technology work? GPS works through a technique called as trilateration, used to calculate location, velocity, and elevation. Trilateration collects signals from satellites to output location information. It is often mistaken for triangulation, which is used to measure angles, not distances. Satellites orbiting the Earth send signals to be read and interpreted by a GPS device situated on or near the Earth's surface. To calculate location, a GPS device must be able to read the signal from at least 4 satellites. Each satellite in the network circles the Earth twice a day, and each satellite sends a unique signal orbiting parameters and time. At any given moment, a GPS device can read the signals from 6 or more satellites. A single satellite broadcasts a microwave signal which is picked up by a GPS device and used to calculate the distance from the GPS device to the satellite. Since a GPS device only gives information about the distance from a satellite, a single satellite cannot provide much location information. Satellites do not give off information about angles, so the location of a GPS device could be anywhere on a sphere's surface area. When a satellite sends a signal, it creates a circle with a radius measured from the GPS device to the satellite. When we add a second satellite, it creates a second circle, and the location is narrowed down to one of the 2 points where the circles intersect. With a third satellite, the device's location can finally be determined as the device is at the intersection of all the 3 circles. That said, we live in a 3D world, which means that each satellite produces a sphere, not a circle. The intersection of 3 spheres produces 2 points of intersection, so the point nearest Earth is chosen. Here is an illustration of satellite ranging. As the device moves, the radius, that is the distance to the satellite, changes. When the radius changes, new spheres are produced, giving us a new position. We can use that data combined with the time from the satellite to determine velocity, calculate the distance to our destination, and the ETA. What are the uses of GPS? GPS is a powerful and dependable tool for business and organizations in many different industries. Surveyors, scientists, pilots, boat captain, first responder, and workers in mining and agriculture are just some of the people who use GPS on a daily basis for work. They also use GPS information for preparing accurate survey and maps, taking precise time measurement, tracking position or location, or for navigation. GPS works at all the times and in most all weather condition. There are five main uses of GPS. Location, determining a position; navigation, getting from one location to another; tracking, monitoring object or personal movement; mapping, creating maps of the world; timing, making it possible to take precise time measurements. Let us discuss about some specific examples of GPS use cases. Emergency response. During an emergency or a natural disaster, first responders use GPS for mapping, following and predicting weather and keep tracking of emergency personnel. In the EU and Russia, the e-call regulation relies on the GLONASS technology, which is a GPS alternative and telematics to send data to emergency services in the case of a vehicle crash, responding response time. Reading more about GPS tracking for the first responders. Entertainment. The GPS can be incorporated into games and activities like Pokemon Go and geocaching. Health and fitness. Smartwatches and wearable technology can track fitness activities such as running a distance and benchmark it against a similar demographic. Construction, mining, and off road trucking. From locating equipment to measuring the improving asset allocation, GPS enables companies to increase return on their assets. Check out on our post on construction vehicle tracking and off road equipment tracking. Transportation. Logistic companies implement telematics systems to improve driver productivity and safety. A truck tracker can be used to support route optimization, fuel efficiency, driver safety, and compliance. Other industries where GPS is used include the agriculture, autonomous vehicles, sales and services, the military, mobile communications, security, and fishing. A brief history of GPS. Humans have been practicing navigation for 1,000 years using moon, sun, stars, and later the sextant. GPS was an advancement of 20th century made possible by space age technology. GPS technology has been used globally throughout history. The launch of Russia's Sputnik 1 satellite in 1957 ushered in the possibility of geolocation capabilities, and soon after, the US Department of Defense began using it for submarine navigation. In 1983, the US government made GPS publicly available but still kept control of the available data. It wasn't until 2000 that companies and the general public gained full access to the use of GPS, eventually paving the way for the greater GPS advancement. Global Navigation Satellite System GNSS. A GPS is considered to be a global navigation satellite system, meaning it is a satellite navigation system with a global coverage. As of 2020, there are two fully operational global satellite navigation systems and the US Navigation Signal Timing and Ranging GPS and the Russia's Global Navigation Satellite System. The Navstar GPS consists of 32 satellites owned by the US and is best known and most widely utilized satellite system. Russia's GLONASS consists of 24 operational satellites with 3 remaining as spares or in testing. Other countries are also racing to catch up. The EU, for example, has been working on Galileo, which is expected to reach full operation capacity by the end of 2020. China is also building the Beidou navigation satellite system with 35 satellites planned to be in orbit by May 2020. Japan and India are also well on their way with their own regional systems, the Quasi-Zenith satellite system and the Indian Regional Navigation Satellite System, respectively. Here are the various global navigation satellite systems. GPS versus GNSS devices. Though GPS is a subset of GNSS, receivers are differentiated as GPS or GNSS. A GPS receiver is only capable of reading information from satellites in the GPS satellite network, while the typical GNSS device can receive information from both GPS and GLONASS at the same time. A GNSS receiver has 60 satellites available for viewing, while a device only needs 3 satellites to determine its location. Accuracy is improved with a large number of satellites. The chart below shows an example of the number of satellites available, along with its signal strength to GPS receiver. In this case, 12 satellites are available. A GNSS device can see more satellites, which helps improve device accuracy. The chart below, there are 17 available satellites. Green bar are the part of GPS and the blue bars are the part of GLONASS. A large number of satellites providing information to the receiver enables the GPS device to calculate location with a greater precision. More satellites give a better chance of getting a positional fix when the receiver has calculated the location of the user. That being said, GNSS receivers also have some drawbacks. The cost of GNSS chips are higher than that of GPS device. GNSS uses a wider bandwidth 1559 to 1610 MHz than GPS 1559 to 1591. MHz. This means standard GPS radio frequency components such as antennas, filters, and amplifier cannot be used for GNSS receiver, resulting in greater cost impact. Power consumption would be slightly higher than with the GPS receiver as to connect to more satellite and run the calculation to determine location. The future of GPS. Countries continue to build and make improvements to their GPS systems. Efforts worldwide are being made to increase accuracy and improve reliability and GPS capabilities. For example, GNSS receivers are expected to become smaller and more accurate and more efficient, and GNSS technology is set to penetrate even the most cost-sensitive GPS application. Scientists and rescue workers are finding new ways to use GPS technology in natural disaster prevention and analysis and the event of an earthquake, volcanic eruption, sinkhole, and avalanche. For the COVID-19 pandemic, researchers are looking at using cell phone location data to assist within the contact tracing in order to slow down the spread of virus. The launch of new GPS-3 satellites will refine GPS accuracy to 1 to 3 meters, improving navigation abilities and long-lasting components as early as 2023. By broadcasting on the L1C civilian signal for the interoperability with the other satellite systems, the next generation of GPS satellites will include better signal protection, decreased susceptibility to signal jamming, and more maneuverability to cover dead zones. The National Aeronautics and Space Administration's Deep Space Atomic Clock is said to use a powerful onboard GPS satellite to help provide better consistency in the time for future astronauts embarking on the deep space journeys.